15 on the
Actually, some people might still be working on it, and so they probably don't want the answer before trying to figure it out. And so, is there a specific? Let me hit a specific point.
Well, I tried to simplify the solution, and it didn't work. So my question was, am I supposed to reset before that to get like a simple version to help me essay? But I could ask you after class.
Well, or post it. The practice test. Let's see. There's still people working on the practice test. Yeah. Okay. Let me hold off on talking about that. But yeah, always try. If you get stuck and something doesn't work, then you try something else. And then, which would be reset. Try that and see. If that fails, then you fall back on successive approximations, right? Okay. And so you want to go through that sequence. You don't have to hesitate in doing. You got to just try to figure out a solution. So if something fails, that often happens. It fails, and you got to keep moving on. All right, Mimi, did you have a question also? 17 on the homework. But post on Piazza and see what other people are doing for solving that, that particular step, or what sequence of steps they did. And I'll chime in. Oh, what was 17 on the homework? Do you have the question? No.
Okay, I wrote everything down, but I didn't know the No, this is No, I found it.
Were there other questions? All right, 17 is very similar to 18 in that there's an ice table and you just have to fill in the blanks. And so was there a specific one that was?
When I got stuck, I got to the end of the ice table and case equals whatever I got, and then I got stuck, like I can't find it. I don't know, should I do some fine?
Okay. PCL5 goes to PCL3 and CL2. Just look. And so we just fill it in with what we're given here. 1.00 times 10 to the minus 3 moles of PCl5 divided by 250 milliliters gives us how many molar PCl5? 0.004. 400. Is introduced into a flask and equilibrium is established. So how much PCl3 do we have
0.
at the beginning? 0?
Yeah.
And chlorine?
9.65. Oh wait, as a moment? Okay. 0.00386.
Do I put that in here on the first line? It's equilibrium, so I can't. So assume that there's 0 here. Right, and so actually the Cl2 we know is going to be down here, which is, what's the molarity?
0.00386.
All right. And then let's fill in the rest. This is going to be minus X molar, plus X molar, and plus X molar.
It's 386.
386.
Yeah.
0.0386 or 00?
0.00386.
Thanks. Let's go one extra. Is there a 0 after that? 386 what?
That's like 6.
Okay. And so can we figure out?
I think that's what I went wrong.
Yeah. And so we could figure 0 plus X is equal to this, so X must be equal to that. And so we'll fill in the rest of
So
it.
even though they give you a whole bunch of values and it says equilibrium, so whatever side that there's 1 0, you just do 0 for the same over.
Yeah, it depends on how the question reads, but typically, yeah. They don't, yeah. Okay, other questions? No. Let's continue with chapter 16. Acids and bases.
Let's say it again.
All right. Now, we did that long problem before. And what we have is, in chapter 16, we have this type of mixture. We're going to have acid plus water and base plus water. Sorry. Acid plus water plus base plus water. And so in this, this is how we're going to handle these. Typically what we'll do is we're going to start off with the biggest K in a mixture. And then we're going to do this stepwise. Step one. To successively smaller Ks. And so start off with the biggest K, then the next biggest, etc. And so the technique here is the stepwise. But sometimes, this is gonna be the easiest to do. And sometimes the stepwise fails, and we have to resort to something called simultaneous. Must do simultaneous. So let me tell you what I mean by the stepwise versus simultaneous. Here. All mixtures containing multiple, interdependent, let's say, interdependent equilibria. Actually, let me be more specific here. Multiple equilibria. Should be solved simultaneous. So all mixtures containing interdependent multiple equilibria should be solved simultaneously. But this is difficult. So what we'll do is we'll try to simplify it. By using the stepwise approach. This is like, sometimes we try to simplify the quadratic equation by using the simplifying assumption, but really you should be solving it using the quadratic, because the simplifying assumption is introducing error. Well, the same kind of thing here. When we use the stepwise method, it's not, it's introducing an error, but sometimes that error is so small, it really doesn't make much difference. And so let's take a look at a mixture here. Let's redo the problem with 0.100 molar HCl. This is the way we're going to handle it. Earlier I was talking with Le Chatelier's, so I was trying to tie it in with Le Chatelier's, but we're going to be doing it a bit differently now. And so what do I have here? Well, when I have an acid like this, HCl is a strong acid, and it's going to look for bases. Now, are there any bases present in this mixture? It turns out there is. Do you know what the base is? Well, it's a substance that can act as a base, but typically we don't call it a base. What do we call it? What else is present? If you were to inventory this, what else is present in this? Yeah, water. Now, can water act as a base? Yeah. So there is a base present. And so this is something you do in Chem 1A. You learn that HCl can react with water. When it reacts with water, it does this. It hydrolyzes water 100%. And so we end up with hydronium and chloride. This is called Ka. A stands for acid hydrolysis. or ionization. It's probably more commonly referred to as acid ionization constant. The Ka is just acid plus water. Acid hydrolysis. Acid plus water. And basically it's just the Kc. C value. The Ka or the Kc value for this is just going to equal the hydronium ion concentration times the chloride ion concentration divided by the HCl concentration. That would be it. Kas are compiled in tables, so we can find Kas in tables. And just use them. And so if we take a look at this table over here on the relative strength of acids and bases. So let's see if I can get that. We start off, here's the Ka. This means acid plus water, or acid hydrolysis, or acid ionization. And it's just the ions over the molecules. So it's a ratio of the ions to molecule that is unionized molecules, or unhydrolyzed, or intact molecules. And so here, do we, if we take a ratio between the ions versus the molecules here, you see that, do you guys see that if I write it like this, H plus perchlorate, it's the same as that equation there. It's because H plus can't exist stably in water, it's going to attack it, form hydronium. And so all these are, HClO4 plus water yields hydronium plus perchlorate. We're going to write it as a hydrolysis equation because it's going to be much easier for us than writing it as an ionization equation like this. But when we look at the Ka, you look at the ratio of ions versus unionized, and these are all strong electrolytes. Strong acids are strong electrolytes, meaning they should be 100% ionized. If they're 100% ionized, then the ratio between the ions versus the intact molecules should be infinity, right? We should have 0 intact molecules and all ions. That's a strong electrolyte. But it turns out that it's nowhere near infinity, actually. But it's a very large number. Not as large as you might think, but large enough that, for the most part, they're completely ionized. And so we're just going to assume complete ionization here. And so when you see a very large K, that means, this is a one-way reaction. This is not really equilibrium. It's just one way. And so what that means is this. Ka for HCl is very large. Very large means complete reaction. It's just one way, basically. And so here, if I start off initial at 0.100 molar here, and I'm going to assume that nothing's reacted. I'm just going to say that if I put in the molecules in there, and this is the way we start every problem, we just assume nothing's happened yet. And then we allow it to happen. There's going to be a change. The change is going to be minus X molar, plus X molar, plus X molar. Normally it's a partial change. Since it's a partial change, we use the variable X because we don't know how much change that is, right? But in this case, it's not a partial change. In this case, it's a complete change, so we do know the value of X. We're going to lose all of it. The Ka is very large. And so in this case, this is going to be minus 0.100 molar. This is going to be plus 0.100 molar. And plus 0.100 molar. And so at the end of this, I expect 0 molar HCl, 0.100 molar hydronium, and 0.100 molar chloride. And so I start off with the biggest K, which would be the Ka for HCl, which is very large. And then I work my way down. When I mean interdependent, equilibria, there's another equilibrium happening here. And that other equilibrium is Kw. And the way these two are interdependent is they have a common species. You know, Ka generates hydronium. Well, in Kw, we also have hydronium. And so when we try to do this stepwise, we call this one step 1 here. And then what we're going to do is we're going to go down to step 2 next. In step 2, the other equilibrium that's happening in this beaker would be H2O colliding with H2O. And so for sure, HCl and H2O is going to be a much more reactive combination, but can you stop H2O and H2O from colliding? No, that's not possible, and this collision's happening constantly, generating hydronium and hydroxide. Normally, we know that this generates 10 to the minus 7 molar, 10 to the minus 7 molar, right? But what's going to happen is we're going to have a Le Chatelier's perturbation of this, which is going to shift it left. But we don't do that. What we do is we just reset this. And so these both are liquid, so we'll ignore those from the ice table. And so if these are both 0, so we'll say 0 molar and 0 molar from water. And so we aren't going to allow the water molecules to collide. We're just going to reset. You know, the 10 to the minus 7, it was 10 to the minus 7, we reset it to the left. Is that okay? The reset. Okay, that's the initial from water. And then the initial from HCl step 1 is going to come in here. Because this hydronium is in the exact same beaker as the water. And so what we're going to do is we're going to move this. We're going to take this hydronium and move it into this equilibrium because there's hydronium present here. That. And there's no hydroxide present. The HCl doesn't add any. And so now I'm going to have the initial total. Pretty soon I'm going to get rid of this and we're just going to drop it. And so the initial total is going to be 0.100 molar hydronium and 0 molar hydroxide. Okay, so I'm carrying that. So this is the same setup as we had last time. The change is going to be plus X molar, plus X molar. So we can solve this pretty quickly again. This is going to be 0.100 plus X molar and then X molar. We know that Kw is equal to 1.0 times 10 to the minus 14, which is going to equal 0.100 plus X times X. And then I'm just going to automatically do the simplifying assumption. You know, the simplifying assumption should work pretty well here because 1, Kw is very small, meaning it should be mostly reactant. We don't expect much product. And 2, the simplifying assumption should work exceptionally well here because we have lots of hydronium to start with. If we have lots of hydronium to start with, then the population, that is, the amount of reaction of hydronium and hydroxide we can generate is not very high because what's going to happen is, as the hydroxide ion concentration gets higher and higher, the hydronium will attack it. You know? And so I use that predator and prey, you know, it's going to keep the prey population down, which is hydroxide because of the predator. We got lots of predator around. Does that make sense for that?
Okay, so for the hydronium, the 100 molar, you put it over there because you said it's in the same container or something. Like, why did you bring the 0.100 molar into the other?
Because if I have a bottle of HCl, right, there's 0.100 molar hydronium around that we're going to generate from this. And so that means that the water, now we have 2 equilibria happening. We have this equilibria and this equilibria. In the water equilibrium, you know, this 0.100, we can't ignore it because it's already in the water. And so since we have that, that's why I moved it down here. If I called it 0 and then 0, then I'm completely treating them separately. But these are 2 interdependent equilibria because they share a common. So do this 0.100 times x, and x is going to equal 1.0 times 10 to the minus 13. Okay, 1.0 times 10 to the minus 13 means that this, this is going to be 0.100 plus point, okay, now I need how many? I need 12 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a 1, 0. And so I'm going to get point 1, and then 11 zeros after that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1. And then over here, I look, the x value is going to be 1.0 times 10 to the minus 13. If there was no hydronium around, then it would, the population of hydroxide would go all the way up to 1.0 times 10 to the minus 7. But here, with this much hydroxide around, hydronium around, the concentration can only get to 10 to the minus 13 because the hydronium's attacking it, and so forcing the reverse reaction to occur. Does that make sense? Or not? In other words, this is what we call common ion. I have a lot of hydronium in there. And so we built up a little bit of hydroxide, not as much as we might have expected. Might have expected like 10 to the minus 7. But here. And how much additional hydronium did we add? We added this much additional hydronium. Was that significant? No. In fact, when you look at the justification for this, we're supposed to justify this by the percent change. And the percent change is going to be equal to the change, which is 10 to the minus 13, over the initial, which is 10 to the minus 1 times 10 squared. And so the percent change is going to be 10 to the minus 10%, which is way less than 5%. With a percent change like this, it would make no difference if you solve it using quadratic versus simplifying assumption. You get the same answer. All right, now we're interested in the pH of this. And often we're interested in the pH. And so pH is equal to the negative log of the hydronium ion concentration. And so we'll plug in the hydronium ion concentration here, and we'll get a pH. What does the pH come out to? Does somebody have it? One point, now we're allowed 3 sig figs, so 1.00, is that 3 sig figs? No, this is a power function. 1.000 would be 3 sig figs. Okay. Because this is the placeholder or the exponent, and everything after that is significant. And so this is 3 sig figs. Because we have 3 sig figs here. Now, we did this using the stepwise approach. And the stepwise approach, we always have to check something when doing the stepwise approach. What we have to do is this is the check to see if the stepwise approach is valid. We have to see if step 2 perturbs step 1. If step 2 perturbs step 1 via Le Chatelier's type perturbation, then it fails. Okay, our step 1 here is easy because of this. Strong acids are one-way reaction. So no matter how much extra hydronium I add to this, it will not perturb. So no matter how much extra hydronium ion concentration does not perturb. So looking at this, what we expect to happen is this. If the hydronium ion concentration increases, then this should shift left according to Le Chatelier's principle. But, you know, when K is very large, what that means is just a one-way reaction. And so even if I double, let's say I double this from 0.100 to 0.200, it has no impact. It does not shift it back left. So Le Chatelier's principle does not work when the K is very large, or the K is very, very small.
Is that only for strong acids though? Like you're saying K
Yeah.
is very large?
And strong bases. Look on the bottom right. What does it say there? Bottom right, the Ka. Very small, which means, we'll talk about it later, but that means that's also one way, but it's one way the reverse. Okay. Well, anyway, strong acids, one way. The other thing is this. Did we really change the, would you call that a significant increase in concentration? This is an insignificant, this would be called a negligible increase in concentration. All right, so one, strong acids, and two, this is a negligible increase. So even if one was a weak acid, so if step 1 was a weak acid that could be perturbed by Le Chatelier's principle, it would still be negligible because the increase in concentration was negligible. No impact because increase was negligible. And so here the stepwise is fine. Stepwise worked, no problem. I'm going to give you another problem now. You know, in fact, did you guys do pH calculations in intro chem? When you did pH calculations in intro chem, do you ever remember solving KW? Doing that? No, you probably just figured, you know, 0.100 molar HCl is going to give you 0.100 molar hydronium. Did you worry about KW? Not at all. And the reason is because, was KW really that significant of an additional, no. And so in Chem 4, or Intro Chem, we always ignored KW. Why? Because introducing KW means extra work, right? Extra hassle. But let's talk about pH briefly before I give you that example. Now, this is a acid solution, but take a look. There's strong base present in this acid solution. And so what is this still an acid? What does it mean to be an acid? An acid shouldn't have a strong base like hydroxide around, should it? Should an acid have a strong base like hydroxide around? I got 10 to the minus 13 molar hydroxide. But this is a strong acid. Did I add any base to this? I didn't add any base. So where did that hydroxide come from? Water. Can I stop the water molecules from colliding? Because I don't want any hydroxide in my strong acid solution. I want full strength acid. Can I stop it from colliding, the water molecules? No, impossible. And so this is what it means to be an acid. To be an acid means that the hydronium ion concentration has to be greater than the hydroxide ion concentration. That's acid. Neutral means that the hydronium ion concentration equals the hydroxide ion concentration. And base solutions will have a hydronium ion concentration that is less than the hydroxide ion concentration. And so this is what it means here. And so typically when we look at the hydronium, let's look at the hydronium. The hydronium, the hydroxide, and the pH. Usually we go with pH instead of pOH, even though they're interconnected here. So let's look at some values here. For this, we're going to have 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar, and the pH is going to be equal to 7.00. That's neutral. If it's an acid solution, then the hydronium goes up, right? So 10 to the minus 3. Let's go to 10 to the minus 3 molar. If we're at 10 to the minus 3 molar, then the hydroxide, these have to add up to 10 to the minus 14, which is KW. So this is 10 to the minus 3, this has got to be 10 to the minus 11. And the exponents need to add up to 14, which gives us pH of 3, right? Etc. We can go the opposite way. Actually, what is this? This goes 3. We could have a pH of 0, right? So if we have a pH of 0, this is 10 to the minus 0. This means the hydroxide must be 10 to the minus 14, so the iota and the pH is equal to 0. Can we go negative? Is that possible to have negative pHs, or is 0 the bottom of the pH scale? I have it inverted here. Are negative pHs possible? This is 10 to the minus 0 is 1 molar. Can I go to 3 molar? Is it possible to make 3 molar HCl? How about 6 molar HCl? Is that possible? How about 12 molar HCl? So if you have 12 molar HCl, what is the pH? Why don't you calculate it? 12 molar HCl is going to give you about 12 molar hydronium. And so what's the negative log of 12? Negative what? Negative 1. Negative 1, what's going on there? Does the pH stop at 0 and won't go beyond that? No. Once we go here, we can go to 0. Oh, we can't really go to 0, can we? We can go to, let's go up. We'll go to 1 molar. Let's actually, this is 1 molar. We'll go to, let's say, 6 molar. if we have 6 molar, then we can figure out what the hydroxide's got to be. But what is the pH? So what's the pH? -0.5? Linear? What's the pH of 6 molar? H plus. Negative log of 6.
-0.7.
-0.7? So why don't we hear about negative pHs much? You know, there's a lot of confusion because a lot of people say we can't go negative, but we can go negative. Negative pHs are possible, right? Because higher hydronium concentrations are possible, but they aren't common in Chem 4 calculations. Do you know why?
Extra work.
Hmm?
Extra work.
Extra work, a lot of extra work, because when solution concentrations get high, we have to worry about something. Do you guys remember about activity? Tell me about activity. Tell me about ideal behavior versus non-ideal behavior. Ideal behavior would be like if you had sodium chloride, right? 0.1 molar sodium chloride, it would split up into 2 pieces and give you 0.2 molar. That's ideal behavior. But sometimes we deviate from that ideal behavior because of... Did you guys read this? Interionic attractions. When the concentrations start to get high, then things start to deviate from ideal behavior because of what kind of attractions? Well, anyway, they didn't talk about this because, you know, really you should use activities instead of ideal concentrations or stoichiometric concentrations. And so that's beyond the scope of Chem 4. And so when you were doing pH calculations, they never went below 0, otherwise you'd be getting the wrong answer. You know, this pH isn't accurate because this isn't exactly accurate. And so once you start getting, whereas these are fairly accurate because the concentrations are small. When the concentrations are small, it kind of behaves ideally, like you'd expect. But when the concentrations start to get bigger, then the solutions start to deviate from ideal behavior, and we have to use activities and all that other stuff at the end of chapter 12. Or was it 12 or 13? At the end of chapter 13. Right. And so in Chem 4, the easiest thing to do is just ignore those. Ignore anything below 0 and ignore anything above 14. Do you think 14 is where the pH scale stops? No, but that's where you're going to get fairly accurate calculations. But beyond 14, you got to use, other tools. And so we can go down, etc. Going down the other way. And so let's take a look at this here. Next. This is where a Chem 4 style calculation will fail. Uh, 1.0 times 10 to the minus 8 molar HCl. What's the pH of this? Use a Chem 4 style calculation to determine the pH of this. You know what a lot of people will tell me? They'll tell me I'm going to get 1.0 times 10 to the minus 8 molar hydronium from this, and therefore the pH is equal to 8.00. Unfortunately, on the pH scale,
pHs less than 7 are called acidic. pHs greater than 7 are called basic. And so this solution should be, we'll call it slightly basic, because really basic is 14.
Is there a problem?
If you add a little bit of HCl to water, it makes the solution basic, correct? Is that right? See, so in Chem 4 you would have never been given this because, you know, the method that you use, assuming that KW is negligible. Although you never had to state that assumption, right? But all the calculations you were doing, you should have stated the assumption that you're going to ignore KW. In this one, no, this is impossible. Impossible. This is acid. Therefore, this is impossible. If it's acid we're adding to water, then the solution should
Come out acidic, not basic.
And so what you have to do is, I know it's a lot more work, but you have to repeat the calculation we just did for this in order to solve it. And so can you do that for me? Repeat the calculation we just did, except using this concentration rather than 0.100 molar, and it works. So do that now.